so I'm going to turn on the recording. So just what I was saying is just a moment ago, right, is I will post the solutions to the exam review sometime tomorrow or Saturday, maybe. When I do that, I'll send a message. But we will have covered all of the types of questions that will be on the exam review, I think, by today's notes, when we get through with today's notes. And then likewise for the homework. So all the things, I think all of the lecture that we have necessary for the homework will be through today. Okay, so we are pretty much right on time for the first test, minus that week that we missed. So so we're doing okay in terms of time. This homework on measuring change, I just pushed that back a little bit, but you should be able to finish that even before today. So because we've talked about everything. We already talked about everything Tuesday that was in this homework, and then again by the end of today's lecture, we will have, I think, done everything that's in this homework on instantaneous rate of change. Okay, and then Madison said next week her sessions will focus on the exam review. So the exam review, in addition to the homework, is really important as preparation for the test, so that you don't get blindsided by types of questions that you're not expecting, and then you don't answer them right, even if you know the material. You're just not expecting the question to be asked in a particular way, and then you miss it, even though you should have, even though you really knew it. Okay, so that's why I really stress going over the exam review. It's now, it seems like it's long, but it's not really that long, because a lot of the questions are really conceptual questions. They don't require a lot of calculation, and so it's not that lengthy to get through. Okay, and then a lot of the questions are duplicate, so you'll see sort of back to back. Two questions will be very similar to each other, and that's just to give you extra practice. Okay, so that also appears to add to the length of the review, but it really doesn't make it any more challenging. It's just to give you extra practice. Okay, so but please do heed my warning to work on the review before it's time to take the test. Okay,
Dr.
Another
Walton,
on Thursday. Yeah, Daniel.
on the exam, like how many tries we have for the answer to answer the questions?
Well, you have infinitely many because the exam is written. So I will post the exam, and then you will write your answers, Daniel, and then you will convert those to PDF. So you'll scan them in some way, right, and then send that back to me. Okay.
Okay, it's not on the website, the exam.
It's not on WebAssign.
Okay.
Yeah, it's not on WebAssign. This will be a written, just like the exam review. It'll be just like the exam review. So you'll write your answers on paper and then send those back to me. Does that
All right, thank you.
make sense? So
Yeah,
it's
yeah,
not a
that-
matter of certain number of tries, right?
Yeah, that makes sense.
Yeah. Okay. Oh, that reminds me now. You should look on Blackboard. I don't have Blackboard up right now, and I'm not going to pull it up. But you should look on Blackboard under the section where it says tests. I think because that's where the test is going to be posted. It's not posted yet, but in there are instructions on how you are going to scan the test and then email it back to me. It's just a matter of scanning it to PDF. You can do that in lots of ways, but you can do it with your phone. And then, and there are plenty of apps for phone that will do that easily. And then you will email that back to me, and then I will grade it. But it does have to be in PDF form. It cannot be a photograph, right? It cannot be like a JPEG file. It has to be in PDF. So you'll have to use either a scanner or an app that will convert to PDF so that you can send that back to me. You'll have a couple of days to do the test, so you'll have time to finish the test and scan it and send it back to me. But you may want to look at those instructions. Again, it's under that test link on the Blackboard page, because that's where the test will be posted. And then under there are instructions for, how you're going to scan it and send it back, which is pretty easy.
What are the dates for the exam again?
The exam will be posted next Thursday,
Okay.
and then you will submit it to me by Saturday.
Okay.
Yeah, so you have a quite a window there to work on it.
Mhm.
It won't take. It's not going to
When
take you. If you work on it, straight, it won't take you any longer than a class period would. It's designed for a class period, but you do have more time.
when we're answering the question on the exam, like we have to answer, put only the answers, or we have to show the work stuff?
Oh no, yes, it's very important that you show work, right? So that's going to be a key part of the test, is showing work. So on your test, you must show work. Now, some of the questions really don't require work, right? Okay, so in that case, you would not show work. But if a question requires some sort of work, right, then it's really important that you show that. And so for two reasons. Number one, you can get partial credit for showing work. But the second reason is if I know a problem requires work and there's no work there, but just the answer, I'm going to assume that you did not produce that answer. I'm going to assume that answer came from a calculator or from a computer, and then I will count off. So you must show work. Now, that doesn't mean you have to show every single detail, but you must show enough detail to justify your answer. Does that make sense?
Yeah, that makes sense.
Yeah, so enough work to justify your answer if work is required. If it's just a yes, no sort of question that really doesn't require work, then you would just answer yes or no. Yeah.
Okay.
So again, use the sample test as a guide for what the questions will look like. And then some of them require some written work and some of them do not. So, okay. So that's another reason for looking at the sample test. So again, you'll have an idea before you start the test. Oh yeah, how much I'm going to have to write down, or how much I don't have to write down. So that may become clear when I post the solutions. How much work would be expected to show on certain questions. But I usually write. I'm going to probably put more detail than you would put. So just if I put a lot of detail, that doesn't mean you have to put that many steps. Okay, other questions like that? All right. Well, we've got up to quite a few participants here. So again, I slightly moved the homework date on the measuring change. A lot of people have worked on that, but I just gave you a couple of extra days, and then today we'll talk about we started talking about instantaneous rate of change last time. We're going to talk more about instantaneous rate of change today, and hopefully finish up all the notes that are necessary for this homework and also for the test. So I think what we finish today will be it for what's on the exam review and for the test. Okay, I'm not gonna go over the homework, so you can ask, but if you've got specific questions, ask me. But Madison will be happy to answer homework questions for you, or you can book an appointment in the Math Center. So look for that announcement on here on the right hand side of the assigned page. There's the link to the Math Center where you can set up an online appointment if you need to ask questions about some of the homework problems. And don't forget, you can email me. You can ask your instructor. So if you're having questions about certain problems, hit that Ask Your Teacher or Ask Your Instructor tab and send that to me. Okay. Colin, you had a question about plus minus. You emailed me and I said, could you send me the problem? Colin, are you listening?
Hi, I'm here. Yes.
Was that plus minus was that in the solutions to an equation? Was that like the solutions to a quadratic equation where you have one solution where you add and one solution where you subtract?
No, it offered a graph that I think I sent you the equation. It was x squared plus something divided by x squared minus. Do you remember that?
You didn't. I don't think you sent me the problem.
Oh.
If you go back to the homework and ask your teacher.
Oh yeah, okay, I'll do that. Yeah.
Yeah, then I can see it and explain it. I don't think, however, in WebAssign, there's a plus minus. So if, as I recall, there's not a plus minus symbol. So I think if you have to enter plus and minus, you'll have to do it with two separate expressions. Write one expression with the plus and then comma, one expression with the minus. Something like that is usually what's required. So that's a little bit tedious, but I think that's what is necessary. I think on the palette, on that math palette on the right-hand side, WebAssign does not give you a plus minus operation. Okay, all right, so let me switch here to the, let me switch to the notes here and.
Oh, Professor, I had a
Uh-huh,
question on homework.
Yeah.
Could we do the measuring change, one of the last two questions?
Are those are computing difference quotients, I think, right?
Yeah.
Yeah, so let me see if I can get this open. And yeah, those are probably the hardest ones. Let's jump right to the oh, here's the real, well, let's do the really hard one. Might as well do the hard one, right? Okay.
Yeah.
So so we want to, this is going to come up again later today, so it's worth reviewing anyway. So they're giving us this function. So this is just a nice quadratic function. Let me write it down so I can refer to it. Mine is, yours is probably slightly different, but the process will be that we go through will be identical. So
Oh, I think I barely replied to that.
right, and so here our function is 8 minus 7x plus 4x squared, and we want to compute this so-called difference quotient. This is really just an average rate of change. Okay, this is average rate of change from the input value A to the input value A plus some increment. Okay, so this would be a number a little bit bigger than A. All right, and so they write it in this unusual way as A plus some little amount. Okay, well, it could be a big amount. The H can be anything at all. All right, but this is the same as computing an average rate of change from the input A to the input A plus H, an input a little bit bigger than A. Okay, so this type of average rate of change has a special name called the difference quotient, but it's really just an average rate of change. And here they're just asking you to calculate the different pieces that are going to be required to compute this difference quotient, right? You have to calculate f of A, you have to calculate f of A plus H, and then you take f of A plus H minus f of A divided by A. That's the final average rate of change. That's the final difference quotient answer. So they've broken it up into 3 parts for you. Okay. All right. So let me change.
There's like a reflection on your.
Let me change the screen sharing here
It's
to the notes that we're going to work on today, which I think is this one. Okay, so remember, this is the example that we stopped with last time about the someone needs to mute their mic for me. Okay, so this is the that's that construction worker example, but let's scroll past that so we can get some blank paper here and I can do this rate of change. All right, so so again, the function that we were given, at least in my homework, was 8 minus 7x minus 4x squared. And then we want to compute this average rate of change, the average rate of change from A, starting at the input A, that could be any quantity in the domain, and then going over to a little bit bigger than A, that would be A plus H. All right. So what this so-called difference quotient is that we're computing is really average rate of change from x equals A to x equals A plus H, a number a little bit bigger than A. Okay, so of course, that average rate of change formula is a slope formula, right? It's a slope of a secant line, actually. F of A plus H minus F of A over, actually, what should be in the denominator here is A plus H minus A, right? But when you compute A plus H minus A, the A's, of course, cancel, and you end up with just H. That's what was in the homework, okay? They had already canceled the A's and just had H in the denominator. All right, so they broke this down. First, they asked us to calculate what's F of A. Well, that's trivial because all you're going to do is substitute A for X, right, in your function formula. So you get 8 minus 7 times A minus 4 times A squared, all right? So that's F of A. That's easy. What's a little bit tougher is F of A plus H. So this is probably where the algebra is going to get into your way a little bit, right? So again, you're going to take A plus H and substitute it for X in the formula for F. So you get 8 minus 7 times X, but now X is A plus H, minus 4 times X squared, but again, X is A plus H. So you get 4 times minus 4 times A plus H squared. And here's where you have to be very careful about your algebra. So, so you want to do this kind of carefully. The first part's easy because you'll just have 8 minus, and then you just distribute the 7. So you have 7 times A, so that's minus 7A, and then minus 7 times H. So that's minus 7H. This is the part that's harder, all right? The A plus H squared. So look, make sure when you multiply, when you square A plus H, remember that means A plus H times itself. So don't write, this is not A squared plus H squared. It's not that simple. So you have to actually write out A plus H times A plus H before you multiply in the 4. So leave the 4 alone for a minute and multiply the A plus H times itself first. So that would be A times A is A squared. A times H is, well, that's A times H, right? Here you have H times A again. I'm going to write it in alphabetical order, though. So I'm going to write A times H, right? So see, I did A times A times H times A. I wrote that in alphabetical order, though, as A times H, and then H times H, which of course is H squared. Don't forget, though, you have minus 4 multiplied times all of this, though, right? So put all of this in parentheses because you've got a next multiplied by minus 4. So we get 8 minus 7A minus 7H minus 4A squared minus 4AH minus 4AH again, and then minus 4H squared. And now you can add some like terms together. So you have 8 minus 7A minus 7H minus 4A squared. These two are like terms. So you have minus 8 times AH minus 4H squared. Oh, there it is. Oh, finally. See, that's the hard part. That's what F of A plus H is. It's all of this. Now, remember, that's only part of the problem, right? We have to take all of this and now put it back into the difference quotient, right? So remember, F of A plus H is 8 minus 7A minus 7H minus 4A squared. Let's make sure we get all of the terms written down. Minus 8H minus 4H squared. And then we're subtracting off F of A. Here's F of A. So you're subtracting that off. Since you're subtracting that, be sure you put it in parentheses. You're subtracting F of A. F of A is all of this. So make sure you put all of this in parentheses after this minus sign. This minus sign and this minus sign are the same. And now in parentheses, put this 8 minus 7A minus 4H squared over. And remember, all of that was divided.
Isn't it 4A squared?
What now?
Isn't it 4A squared? 8 minus 7A
Yeah,
minus
it's 4A squared, right? So those are the sorts of algebra moves, you know, you can make, right? So be careful of things like that, all right? Okay, let's see now. So we have 8 minus 7a minus 7h minus 4a squared minus 8ah, this is hard to say, minus 4h squared. Now you're going to distribute the minus sign, so you get minus 8 plus 7a plus 4a squared, all of this divided by h. Now, if you're lucky, you should have a bunch of cancellations here, okay? So this is typically what's going to happen in a difference quotient. So notice that these two terms cancel each other, right? And there's a minus 7a and there's a plus 7a. So those go away, and there's a plus 8 and here's a minus 8. So those cancel. So what am I left with? I have to be careful here. I have minus 7h minus 8ah minus 4h squared, and that's it, right? Because these terms all canceled, all of this divided by h. So see, we've already simplified this quite a bit. And now you can simplify it more because h, fortunately, will divide into all three terms in the numerator. So you can divide this h out. You can divide this one out with this h, and h squared over h will eliminate one of the h's here. So what is this reduced to? Minus 7 minus 8a minus 4h. That's it. See, it doesn't work out. Once you do the algebra, it doesn't really work out all that badly, okay? There's the final difference quotient or average rate of change, okay? Same thing. All right, Lance, so did you see that, all of that?
Yeah, I saw all of it. I appreciate
Yeah.
it.
So now so when you're duplicating this in your homework, right, you just have to be very careful to do your algebra properly.
Yeah, the
right?
algebra mistakes.
Yeah, algebra. Yeah, this is this type of difference quotient is like some of the worst algebra we'll have in the course, actually. So it doesn't really get a whole lot worse than this. You'll be happy to know. I mean, there is a lot more algebra in the course, but that's fairly complex in terms of the algebra that we'll have to do. Okay, all right. So I'm going to scroll back up now in the notes, and because I want to resume where we were last time, and we were talking about this screwdriver problem, remember? And we were trying to calculate what was the speed of the screwdriver right after 2 seconds. Okay, so if we had a speedometer on the screwdriver when it was falling. Remember, the screwdriver was falling from a building. A construction worker drops it off of a building that's under construction. It was falling up from a height of 400 feet. And so we were wondering after 2 seconds, exactly after 2 seconds, how fast was the screwdriver dropping? So if we had a speedometer on the screwdriver and we looked at it after 2 seconds, what would it show? Okay, and we were able to actually answer that question last time, or get a really good estimate for the answer to that question, which is kind of amazing, by sort of turning this curve, which this is not the path of the screwdriver, right? But this is the graph of the function that gives the height of the screwdriver after a given number of seconds, okay? When we turned that curve into a straight line and computed the slope of that straight line, we convinced ourselves, right, just by using our logic and intuition, that the slope of that straight line would be the speed showing on that speedometer after 2 seconds. And the way we turn the curve into a straight line, of course, the curve is not a straight line, so we cannot bend it into a straight line, but sort of the way we turned it into a straight line was by zooming in on this piece of the curve right around 2 seconds. This is, I keep pointing at this point, which doesn't have coordinates on it, but this is the point on the graph that corresponds to exactly 2 seconds after the screwdriver has dropped, okay? So when we zoomed in on this little piece of the curve, very close to x equals 2, and we notice that when we zoom in close enough, that curve appears to be a straight line, okay? And so the curvature is sort of invisible to us when we zoom in close enough. The curve appears to be a straight line, and so we can then assume that it behaves like a straight line. And you know, straight lines have steady rates of change, right? So we knew that the rate of change, the steady rate of change, in other words, the slope of that straight line, would be the answer to our question: how fast is the speedometer dropping after 2 seconds? Now, we're going to do this. We're going to duplicate this process again, because I want to answer how fast is the screwdriver falling when it hits the ground. It hits the ground after exactly 5 seconds. And so we want to see how fast was it going when it hit the ground. But before I do that, just one other question that we already know the answer to. When you zoom in on that, piece of the curve, so that it appears to be a straight line, that straight line that you're looking at, that you think you're looking at, right? Okay, has a name. Okay, what is that? What is that straight line called? We talked about this earlier in the semester. So what is the straight line that duplicates a portion of a curve? Remember what such a line is called? What now?
Secant line.
No, a secant line, good answer, Van, you're close. Remember, a secant line connects 2 points on a curve. So here's an example that I'm pointing to. Here's an example of a secant line that's connecting, well, you can't see the first point, but right here, these, the line here that I've drawn right here, Van, that connects these 2 points on the curve, that's a secant line. Okay, so if you pick 2 points off of any curve and draw a straight line connecting them, you get a secant line. But what is the line that duplicates a curve close to a point? So see, looking at this point, this is the point where x is equal to 2. I forgot what the matching y coordinate is. Okay. We could figure that out pretty easily. But this Van, when you zoom in on this point, right? When you zoom in close enough, that curve begins to look like a straight line. That curve duplicates a straight line. So, and we talked about earlier in the course, right? What a curve that duplicates a line that duplicates a curve close to a particular point is called.
Tangent?
That's a tangent line, right? Okay. So what we were really looking at when we zoomed in on this point, so that it looked like a line, what we were really looking at was the tangent line to the curve at this particular point. If I draw that by hand, by the way, I can sort of draw this by hand, even though I can't zoom in on this this curve, but I can draw that tangent line by hand. I think it looks something like this, right? Okay. There's the tangent line to this curve right at this point, because right around that point, this curve duplicates this line, right? Or you can say it vice versa. Right around this point, this line duplicates this curve. So, so what we were using to answer our question last time of what was the speed of the screwdriver after 2 seconds, what we were using was the slope of this. What we were using was the slope of this tangent line. Okay, the tangent line to the curve at this particular point. Okay, that's a very important. All right, I need to repeat. That's a very important concept in calculus. Okay, is again that a tangent line duplicates a curve at a particular point, and the slope of the tangent line, right? Okay, the slope of the tangent line at a point is the same as the slope of the curve at that point, okay? Or we're going to assume that the slope of the curve at a point is the same as the slope of the tangent line at that point, okay? I can't, that sounds kind of like a not very consequential statement when I make it, but that's really almost the fundamental idea in differential calculus. Okay, all right, so enough of me talking there. Let's go back and actually do this problem that I mentioned. So I want to know how fast was the screwdriver falling after 5 seconds. That's when the screwdriver hits the ground. So when we answer the question here in F, we're going to also be answering the question in G, okay? Because it takes 5 seconds for the screwdriver to hit the ground. The reason you know that is because if before we calculated F of 5 and F of 5 turned out to be 0. So that means after 5 seconds, the height of the screwdriver is 0. In other words, it hits the ground after 5 seconds. Okay. All right. So how do we go about trying to answer this question? All right. Let me switch to back to sharing the whole screen to you. And we're just going to go through the same process that we went through last time. Okay. So we can really do this pretty quickly. I need a graph of the curve. Okay, so here's my graph of this curve. So that's the same curve that we were looking at a moment ago when I was drawing that tangent line. Okay, except now we want to see what the tangent looks like, what the tangent line looks like over here at 5 seconds, because this is when the screwdriver hits the ground. This is when the screwdriver hits the ground, right? So what I'm going to do is I'm going to find that tangent line, or I'm going to look for that tangent line by blowing up this curve here close to 5 seconds until the curve looks like a straight line, okay? And that straight line that the curve appears to be is going to be the tangent line, okay? Because again, the tangent line duplicates the curve at a particular x value, or vice versa. The curve duplicates the tangent line at a particular x value. All right, let me start blowing up here. And so I want to make sure I keep 5 in my picture, though, because that is the, remember, that's the x value. That's the time that I'm interested in, right? Have I gone far enough, guys? I mean, just in your opinion? I want to keep going until what? I mean, I want to keep zooming in until what happens?
Until it looks straight, right?
Until it looks straight. Yeah, sure. Right. Okay. Until it looks straight. And now, of course, that's a subjective judgment, right? Okay. So, you know, zooming in until it looks straight, some people might say, yes, that looks straight. Some people might say, no, I don't think that looks straight. But most people would generally agree, okay, that does that look straight to you? I don't know who answered me there. Should I quit, or y'all want to keep zooming in?
I think that looks straight.
Okay, all right. So I do too. All right, so I agree that looks straight. Okay, now, but I want to point out, okay, that there's no reason we cannot keep zooming in. All right, so we could keep zooming in until we break the computer. All right, okay, and in our mind, you know, I don't know how robust Desmos is, but our minds are very robust. So we could keep in our mind zooming in indefinitely. All right. So I want you to keep that little fact in mind. Okay. There's no reason that why we can't keep zooming in, you know, as long as we like. All right. At least in our mind, we can keep zooming in as long as we like. Right. Okay. So now, but let's stop there. So I think this looks straight enough to me that I think I'm going to get a good estimate for how fast the screwdriver is going when it hits the ground. And that estimate for how fast the screwdriver is going when it hits the ground would be what? What would I find in this picture to answer my question?
The slope?
The slope, right? And define, so you want to find the slope of that quote unquote line, right? So I'm pretending this is a straight line. Certainly looks like a straight line to me, right? Okay. We can make it, again, we can make it as straight as we want by zooming in more and more, right? Okay. But this seems sufficient for a good estimate. So how do I find the slope, Van? What do I need?
You need 2 points on
You
the
need 2
line.
points, right? Okay. 1 point you have very easily. This point right here, okay? You know that point is on the line, right? Okay, because that's a point on the curve, and we know the coordinates for that point, right? So y'all write that down for me. 1 point there is 5, 0, right? Okay, so there's a point, and I need another point. So let's see if we can find another point here that we like. What about right here at 4.9? So let me click on that. And let's see what, let's see if I can get really close to that. Let's see what, there it is. Desmos says there is 4.9. So the output that matches 4.9, in other words, the height of the screwdriver after 4.9 seconds was 15.84 feet. Okay, so I'll write that down for me also. 4.9 and 15.84. And now just calculate the slope between those 2 points. That would be the slope of the tangent line, okay? And the slope of the tangent line is going to be our estimate for how fast the screwdriver was dropping after 5 seconds, okay? Because this lines have steady rates of change, right? And if this is indeed a straight line, it's very close to a straight line, so we can treat it like a straight line. It will have a steady rate of change, and its steady rate of change is its slope, correct? So the steady rate of change of this line would be this the rate of change here after 5 seconds, correct? In other words, when the screwdriver hits the ground, okay? Well, the rate of change is the slope of the, I'm sorry, is the speed of the screwdriver, correct? When it hits the ground. All right, so let's do that. Let's switch back now and do that calculation really fast, right? Okay, so see, this is with the computer, right? This is all pretty straightforward, right? So we know that the speed there is going to be what? That the slope of that tangent line. Let me fill in what I just said. So the slope of the tangent line is going to be our answer, and so our 2 points were what we wrote down earlier. Remember, that was 5 and 0. And the point we chose off of the curve was 4.9 and 15.84. So let's see, we get 15.84 minus 0, right? There's the difference in the y coordinates, right? Divided by what? 4.9 minus 5. So we get 15.84 divided by 0.1. That's negative, right? Okay, and it's pretty easy to divide by 0.1, right? That's the same as just multiplying by 10, correct? So it looks like I'm going to come out with what? Minus 158.4. Okay. Did I do that right? Did y'all agree with did I appear to do that arithmetic correct? Is there any disputes with that?
No.
Okay, so so there's our there's how fast the screwdriver was going, right? It was dropping because this is negative, right? So it was falling, obviously, right, when it hits the ground, and it's falling at a rate of 158.4 feet per second. All right, because our height was measured in feet and our time is measured in seconds. 158.4 feet per second. Wow, that is that's pretty fast. And right, So you don't want to be standing underneath that screwdriver, right, when it hits the ground, because it's going to hit you with pretty tremendous velocity there, right? 158.4 feet per second. That's not slow, okay? All right, now, that rate of change that we just calculated, right, after exactly 5 seconds, okay, we're going to, as I mentioned last time, we're going to call that the instantaneous rate of change, all right? So we have now 4 different ways of measuring change in a function. We have the net change, right? We have percent change. We have average rate of change. So remember, the average rate of change tells you on average, right, how the y values are changing from initial x value to a terminal x value, right? So average rate of change tells you how the function is changing, or how the outputs from the function are changing over an interval from a starting x value to an ending x value, okay? What we are calculating is called the instantaneous rate of change. So that tells you how fast the function outputs are changing at a particular x value, not from one x value to a second x value, but at a particular x value. So at one particular instant, at one particular x value, the instantaneous rate of change tells you how fast a function's output are changing. All right. So do you understand the difference there between average and instantaneous? Average is what's happening on average from a beginning x value to an ending x value. But instantaneous rate of change is what's happening at one single x value. Okay. Not from an x value to a second x, not from a beginning x value to a second x value, but just at one x value. Okay. Well, let's try another example here really quick. So with Desmos, this is pretty easy to do. So oh, by the way, here is what I just said, okay, in the notes, okay? So if you have a function, f of x, just some function, then the instantaneous rate of change at a particular x value, not from x equal a to x equal b, but at a particular x value, okay, that tells you how rapidly the function is either going up or down at that particular x value, okay? Or you can also interpret that as the slope of the graph at that particular x value. Okay, I put slope in quotes here because slope is really a concept that we apply to just to straight lines. Okay, but loosely we can say that the instantaneous rate of change of a function at a particular input is the slope of the graph at that particular input. Really, it's the same as the slope of the tangent line at that particular input. Now, here's a piece of notation that's really important, okay? So pay close attention here. We're going to use a notation for instantaneous rate of change, all right? And in fact, we're going to use function notation for instantaneous rate of change. All right, so remember, if you have a function f, right, and some input, remember f of a, that just means the output at the input a, right? So that's the y value that matches x equals a. But if you put the function name and then you put this apostrophe up here, which you don't read as apostrophe, you read it as prime, okay? So you would read this off of the page as f prime of a. That's going to be our calculus notation for the instantaneous rate of change at the input a. Or loosely, you can call that the slope of the graph at the input a. All right, so you see the difference now between these two pieces of notation. The only physical difference is we included this prime mark here, all right, above the name of the function. But the meaning is much different. This means the output of the function at the input a, You know how to calculate that, right? You would use your function formula, or you would use your graph. This means the instantaneous rate of change of the function at the input A. Okay, how fast the function is increasing or decreasing at the input A. Okay, so this is how what's the value of the function at the input A. This is how fast, what's the y value of the function at the input A. This is how fast the y values are changing at the input A. Okay, so be very careful to look for this now in function notation, because we're going to use this frequently. Okay. Now, unfortunately, I have to show you one other piece of notation. Calculus has been around for a long time, but function notation has not been around as long as calculus has been around. Okay, so we have some old-fashioned notation also for instantaneous rate of change. All right, here's the old-fashioned notation. All right, you would write d, and then whatever your output variable is, so usually that's y, right? And then you write this as a fraction over dx, d, and then whatever the input variable is. And then you put a vertical bar here, and then you put x equal to whatever x value you're dealing with. All right, these two things mean the same. Okay, these both mean instantaneous rate of change, or they mean the slope of the graph at the input A. Okay, so this one looks very clumsy, and it is very clumsy. So that's why modern function notation is very nice to have. Okay, but this old-fashioned notation is still used a lot because it's actually very useful in certain instances. All right, you're going to learn about that in Calculus 2. This old-fashioned notation turns out to be have its moments, okay, where it's quite convenient as opposed to more modern function notation. So you might see me using these two things interchangeably. All right, they both mean instantaneous rate of change, okay, or slope of the tangent line. And we have another term for instantaneous rate of change also that we use, and that is derivative. All right, so if you hear me use the term derivative, that means instantaneous rate of change, not average rate of change, instantaneous rate of change. All right, let's try another. Where are we here? Okay, well, let's do this very simple thing to start with. All right, this is not instantaneous rate of change. Here we have this function, f of x is x cubed minus 5x, x cubed minus 5x. And I just want to find, so this is not instantaneous rate of change. I just want to find the average rate of change from x equal minus 3 to x equal minus 1. All right, so can you guys do that? Okay, so average rate of change from x equal minus 3 to x equals minus 1. So try calculating that for me, right? Remember, here's our notation for average. There's our notation for average rate of change. Samir, I may ask you this one, so try computing that.
Yes, sir.
So remember the formula. It's really just the slope formula, right? So in this case, your x2 is this number and your x1 is this number. This is where we started, and this is where we finished. So I don't want to take too long to do that. So I'm going to rush y'all a little bit. Zamir, I'm going to rush you a little bit. So, but that's okay. We'll do this together. So Zamir, let's calculate this. So f of x2, that would be f of -1, right? So that would be -1 cubed minus 5 times a minus 1. Zamir,
So that'd be 4.
what's -1 cubed?
-1.
Yeah, that's -1. And then -5 times -1 is +5.
+5.
So you end up with 4.
Mhm.
All right. Were you able to calculate before I stopped you there the f of -3, since the x1
Got-
is -3 here? What?
Yeah, I got 6.
It comes out to be 6.
I think. Let's see. -3. Oh, no. That's wrong.
Okay. So we have
Sorry.
-3 cubed minus 5 times a -3. So -3 cubed is -27.
Yeah.
Yeah. And then
I did
-5
-9.
times -3 is what? +15.
Yeah.
So we end up with 12.
12. Yep.
Yeah. So close there, but
-12, right?
yeah, -12, right? So, all right. So now let's just plug that into our, let's just plug these numbers into our, formula. So f of x2 there was 4, right? And then f of x1 was what we just found there, what, -12?
-12.
I have 4 minus a -12, and then all of that over what, -1
-3.
minus a -3.
-1 minus -3. Yes, sir.
So we end up with, oh, this is pretty easy. What, in the top, what?
16
16
over 2. 8.
over 2. Yeah. Okay. So, and that's just 8. So the average rate of change of this curve, be nice if we could see what this curve looks like. We'll look at that. The average rate of change of that curve from x = -3 to x = -1, that is 8. I don't think I have a graph of this one. No, I don't. Okay. But I have it on, hang on a minute. We'll look at it. All right. So there's our average rate of change. All right. Let me switch here to, so actually here is this curve, and we just found the the average rate of change from this point, because that's x = -3, that point, which was we got it to be -12, right? And then up to what, x = -1 right there. So somewhere in here, there's x = -1 right there, right? Okay, which turned out to be 4. So what we were calculating is the slope of the secant line that connected these. I don't have these 2 points drawn in, but the slope of the secant line that was connecting these 2 points, that's the average rate of change. So if you draw a point from here at x = -3 up to here at x = -1, if you draw that secant line, that average rate of change was the slope of that secant line. Does that make sense, Amir?
Yeah.
All right, but now here's what I really want to know. So we know on average from x = right there, from x = -3 to x = -1, on average, that a y value was increasing by 8. The y value was going up by 8 whenever x increased by 1, right? So that's what was happening on average. The y was increasing by 8 when x increased by 1. Well, you know, we can see the y values were increasing, right? Because we're going up from here to here, correct? Yeah. Now, but here's what I want to know, Zamir. Right at this point, so right here at -2, right, which is between -3 and -1, I want to know. So right there at -2, I want to know right at that instant, how fast is the curve changing? Is it going up or is it going down, by the way?
Up.
It's going up, obviously, right?
Yeah,
Okay.
yeah.
So right there at -2, it's going up, but I want to know how fast is it going up right there at -2. So I want to know what's the instantaneous rate of change right at -2. Okay. So we know what happened on average from -3 to -1. I want to know what's happening right at -2. Okay. So how do I do that, Zamir? We're going to come back and do it in a second. We'll take a break here,
Okay.
but can you describe the process for me? What do I do?
You would use the derivative, the f prime.
Yes, yeah. So my notation for the instantaneous rate of change is f prime. So what I'm calculating here is f prime of -2. But how would I actually evaluate f prime of -2, Zamir? How would I actually compute that? So what do I do with the graph to find that?
Zoom in.
I
Find a
zoom
straight
in.
line.
Perfect. I zoom in until I see a straight line, correct? Because,
Yep.
and what is that straight line that I'm going to be looking at when I zoom in? What's that
The
straight line
tangent
called?
line.
The tangent line, right. So what I'm really looking for is the tangent line, okay?
Okay,
So
yeah.
that's the line that duplicates the curve. That's the line that duplicates the curve, or that's the line that the curve duplicates right here at -2. And we
Yeah.
find the slope of that tangent line, okay? All right, let's stop for a minute, because so let's take about 5 minutes. We'll come back at 12:35 and then we'll actually do that. So we'll zoom in here, and but that zooming in process is pretty easy, okay? All right, that's all straightforward once you've got the computer, right? Okay, okay, so let me turn off the recording here for a moment. We'll stop for 5 minutes here and catch our breath. And okay, so I'm going to resume now. So we wanted to actually finish and calculate our instantaneous rate of change here at -2. So our task here is to just find the tangent line, right? And by zooming in on the curve here around x equal -2 until the curve looks like a tangent line, until the curve looks like a line, which will be the tangent line. Let's see if we can make that happen. And sometimes that's easier than others because it depends on a little bit on the concavity of the curve. If the curve is very concave, has a lot of curvature, it's hard to make it look like a straight line. But here I think I've got it. All right. So all right. So there I think the curve looks like a line now, right? So I think we're looking essentially at the tangent line. And now all we have to do is pick 2 points off of the tangent line, right? Okay. And then find the slope between those 2 points. And that will be it, right? That will be the what we're going to call the instantaneous rate of change at the input -2. If you want to, let's find what the output is at -2. So here's the exact point on the curve. It happens to be 2. So let's put that down. -2 and 2, right? Okay. And then now let's pick off another point on the curve, and you can really pick off any other point that you like. All right. So let's try here at -1.99. So I'm trying to point at -1.99. Let's see if we can get it. I may have to. There we go. All right. So there's. Oh shoot! I lost it. Yeah, there's -1.99, and so the matching output there is 2.0694. So -1.99 and 2.0694. So there's a second point on our tangent line, right? A second point on the curve, but close enough to -2 that the curve appears to be a tangent line. So we're going to calculate the slope between those 2 points. And that will be our estimate for f prime of -2, the instantaneous rate of change, or the derivative. There's our other terminology here, of the function f at -2. So let's see if I can fill those values in correctly, right? So I have 2.0694 minus 2. That's the difference in the y coordinates, over the difference in the x coordinates is minus 1.99 minus a -2. Okay, so we end up here with, in the top, 0.0694, and in the bottom we end up with what? What is that? 0.1. Did I do that right? I think so. These two things are 1/100th apart. Here we have 0.0694, and it's easy to divide by 0.01. When you're dividing by 1/100th, that's the same as multiplying by 100. So we would end up here with 6.94. Okay. Let me make this approximate. All right, because so I'm going to put that little squiggly line there, just to indicate that this is our estimate for the instantaneous rate of change at x = -2. You know, if we had zoomed in a little bit closer, right, we might have gotten a slightly different value here for the instantaneous rate of change. Okay, so this is only going to be an estimate for the perfect value of the instantaneous rate of change. We're going to try to develop a way, though, of calculating that instantaneous rate of change exactly. Okay, so can we find exactly the tangent line and exactly the slope of the tangent line at a particular input, right? In this case, x equals -2. Let me check my work here to see how close I think I was there. Yeah, that's pretty close. All right, so we did a good job of estimating that instantaneous rate of change. Remember, there's another way of denoting this instantaneous rate of change. The old-fashioned way of denoting this would be, right, dy over dx. That means derivative or instantaneous rate of change. And we found the instantaneous rate of change. We put this vertical bar, and then as a subscript here, we write x equals -2. So this means the instantaneous rate of change. The vertical bar means at, and then x equals -2. And again, that's kind of the original old-fashioned notation for derivative, but still widely used. Okay. All right. So some parts of this example, let me skip. Let me go down here now to a little bit more, because this is just a repeating, finding an instantaneous rate of change. Okay. So for the moment, let me skip that one and let's go down to this question, where we're not going to actually compute instantaneous rates of change, but I'm going to ask you some questions about instantaneous rate of change from looking at a graph, right? So y'all see that graph there. All right, so here are the questions that I want to answer. And the first questions are really easy. So you don't need to know calculus to answer these questions. These are just true or false questions, or yes or no questions. First thing I want is f of -2, is that greater than 0? Is that true or is that false? Notice there's no a prime here, right? So this is not a question about rate of change. I just want to know, is f of -2 greater than 0? Or maybe it's not. What do y'all say to that? From
I'll
looking
say
at the graph.
true.
Well, Assad, you said true. Why true? So why did you think that was true?
Saying that all the y values, meaning f of x values, are greater than 0. So when I look at -2 of x value, I see that everything above that, all the y values are greater than 0.
All the y values are greater than 0. Let's see. That's not what I see. Here's -2, right? And so there's -2. So to find f of
Oh, I
-2,
feel like this is a little bit
to find
like
f of -2, right, you go up or down until you hit the graph. Until here, in this case, you're going down, right? So, and then when you come across, it looks like you're at about -1. So it looks like that is false.
oh, I see.
See what I'm saying?
Yeah, okay.
Yeah, okay. I think f of -2 is false. On the other hand, Saad, what about f of 3?
Looks like 3 would be true because 3 is all the
Yeah.
way down there. All
Yeah,
the y
here's
values.
3. And so when you compute f of 3, right, you're going to go up here, right? And
Right.
that's going to end up, I'm not sure where that ends up. Looks like it's around 4 or 5, right? But it doesn't matter exactly what the value is. It's greater than 0, right?
0, yeah.
So this is true. Okay. So that one we see is true. All right. Now let me step it up though. I'm going to make it harder. All right. Oh no, maybe I'm not. Okay. So f of 5 greater than 0. Maybe that's a trick question. Is f of 5 greater than 0? So there's the graph.
If the graph is continuing, then looks like it would be.
But does the graph continue?
Both side has like the point, so it doesn't continue.
It doesn't continue, right? So it looks like the domain here ends at 4. And so that means there is no f of 5, right? Okay. So this was a trick question. F of 5 is undefined. So I guess you could say false because undefined wouldn't be bigger than 0, right? But the really correct way to answer that is f of 5 is undefined. Okay, so this inequality doesn't make any sense. All right, now let's see about this one. The average rate, oh, so here's the graph again, so we can see this a little bit better without scrolling around. So there's the graph, and I want to know, is the average rate of change from -2 to 0, average rate of change from -2 to 0, is that greater than 0? So this is average rate of change from -2 to 0. Is that greater than 0? So we don't really have to perfectly compute the average rate of change because remember, average rate of change corresponds to slope of what sort of line?
Straight line.
Yeah, straight line, right? But be more specific. What type of straight line?
Linear.
What?
Linear.
Yeah, someone said it. What?
Linear.
Well, yeah, lines are linear. But what type of linear line?
Tangent.
Close. This is average rate of change. Average rate of change is not a tangent line, but what kind of line?
Oh, secant.
Secant, right? Yeah. So average rate of change is slope of a secant line. Secant line. So how do we get that secant line? You're gonna remember connect these 2 points on the curve, right? So you're going to connect the point where x equals -2. That's right here to this point where x equals 0. That's right there. So if you draw that secant line, it looks like this. And is that slope positive or is that slope negative?
Negative.
Negative. So it can't be greater than 0, right? Because it's got to be negative. So the answer here is false. What about average rate of change from 1 to 3? From 1 to 3. Where's 1 on here? I can't see very well. So average rate of change, let's erase this. Oh, that's 2, okay? So average rate of change from 1 to 3. Here's 1, and here's 3. So remember, average rate of change corresponds to slope of what? What kind of line? We just said it.
The secant line.
Secant line. So let's draw the secant line here. All right, so let's go down. There's the y value that corresponds to 1. Here's the y value that corresponds to 3. You draw a secant line between those 2 points. You get this secant line, something like that. And is that positive slope or negative slope?
Positive looks like.
Positive, right? Okay, so this is true. The average rate of change from 1 to 3 is greater than 0. We could calculate it exactly if we knew what the coordinates of these 2 points were, right? We would just find the slope between these 2 points. But we don't need that much detail just to answer this question. All right, now let's look at F. Okay, so now here I'm taking it up a notch. All right, this is not F of -3, but this is F prime of -3. Here's -3. How do we answer this question? So what are we looking at the graph to answer this question? What's that asking us there? This means not average rate of change. This means what? What type of rate of change is this with the prime on it?
Instantaneous.
Yes. So how do we decide, just from looking at the graph, how do we decide if the instantaneous rate of change right here at -3, how do we decide if that's positive or if it's negative? Or it could be 0, but how do we decide what its sign is going to be? Positive or negative 0? Instantaneous rate of change is the same as the slope of what? What line?
Secant?
No, that's average rate of
Tangent.
change. So instantaneous rate, say it again.
The tangent line.
Tangent.
Tangent line, right. So let's look at this and imagine what the tangent line is going to look like. I can kind of sketch it in there. We really don't have to sketch it in, but I can kind of sketch it in. This is kind of what the tangent line is going to look like, right? I drew a really ugly tangent line there, but anyway, kind of like this. And what you're interested in is the slope of the tangent line. Slope of the tangent line. Is that going to be negative or is that going to be positive?
Negative.
Negative. So this is false. It's not bigger than 0. Actually, you don't really have to even sketch in the tangent line to answer this question. You can see that the curve is falling right here at -3, right? The curve is falling. It's decreasing. If the curve is decreasing, that means the instantaneous rate of change is negative. The instantaneous rate of change is going to be negative. If the curve is increasing, the instantaneous rate of change is going to be positive. So what about this? F prime of 2. F prime of 2. Is that positive or is that negative? Let me erase this secant line. There's 2. So there's the point on the graph where x equals 2. So is the instantaneous rate of change going to be positive or negative there?
The tangent line is going to be on the outside, so it's positive.
That's right. The tangent line is going to look something like this, right?
Yes.
And that has positive slope. Or you can also answer this by saying, oh, the curve is increasing right here, right? This graph is going up. And if it's going up, that means the instantaneous rate of change must be positive. So this is true. All right, so this is a trick question now for you. So f prime of 0. So there is right there, there's the point that corresponds to 0. What's happening right here at 0? What kind of point do we have right there?
A local min.
We have a local min. That's right. We have a turning point here. If you draw the tangent line right here, guess what it's going to end up looking like? It's going to end up being a horizontal line. Okay. The tangent line right there is going to end up being a horizontal line. And what's the slope of horizontal lines?
0.
0. Yeah. Slope of horizontal lines is 0, which is not greater than 0. So this one is false, just barely false, but this is false. The tangent line here is has slope 0. That's going to be a real important fact to us. The fact that at turning points, tangent lines have slope 0. That's going to be a very important clue in helping us find turning points. Okay. All right. If we don't have a graph, if we have a graph, we can just see the turning point. But if we don't have a graph, we can, we're going to be able to find turning points by looking for where the tangent line or where the instantaneous rate of change is 0. Okay. All right. Let's switch to our next notes. I've got some more questions kind of like these. All right. So in the next notes, so this is the next notes. Here's a description again of what tangent lines and secant lines are. So we've already discussed that at length. So I don't need to go back through the definition of what tangent lines and secant lines are. Okay. Here's a picture of some tangent lines and secant lines. So there's a curve, and here's an example of a tangent line, right? So this would be the tangent line at x equals a. Here's a secant line, right? Because it connects these 2 points on this curve, right? Okay. So you've seen, we've seen lots of examples already now of secant lines and tangent lines. But here's now the question that I have for you. I've drawn this graph, and I've drawn in a bunch of lines on the graph in red. So here's my function f, that's the black curve. So we got a nice wiggly curve here. It's increasing and decreasing, right, as we move from left to right. And then I've drawn in some red lines here at particular points, A, B, C, D, and E. And what I want to know is, for those 5 points, have I drawn in the tangent line, or have I drawn in some other sort of weird line that's not a tangent line? Okay, so let's start here with this point A. This looks like an x-intercept for this graph. That's not important, but this point here, A on the graph. So I've drawn in this red line. Is that the tangent line to the curve at this point? So have I drawn this tangent line correctly, or have I drawn some weird line that's not a tangent line? So what do y'all say? Tangent or no tangent?
No tangent.
Yeah, that's not going to be a tangent line, right? Okay, yeah, that cannot be a tangent line. Remember, the tangent line has to look like the curve has to duplicate the curve at the point, right? This curve is not straight up and down at this point, right? This curve looks something more like this, right? So I did not do a very good job of drawing the tangent line here at the point A. What about at the point B, though? Okay, so that red line right there, does that look like that could be the correct tangent line? So at the point B, does this red line sort of duplicate the graph?
What was your question again, Professor?
Yeah, so the question is, at this point B, I've drawn this red line here, right, that goes through this point B. My question is that the tangent line at the point B, or could that be the tangent line at the point B? Or have I drawn a line that there's just no way that's the tangent line? So have I drawn a good tangent line or not? Kind of is
actually looks like a secant line or something.
So you remember, you're just asking yourself, does this line duplicate that curve at this point? Not far away from the point, but at this point, does that line more or less duplicate that curve at that point? Colin, did you say something?
I think it does not. It makes me suspicious because it crosses the line.
I mean, because it crosses the curve?
It crosses the curve at that point, which is
at
suspicious.
That point. It cuts through the curve at that point?
Right.
Yeah, normally that doesn't happen with tangent lines. Yeah, so that is kind of suspicious. But if you were to zoom in on this point, we can't zoom in on it, right? But if we were to zoom in on this point, would the black line and the red curve sort of coincide? Would they duplicate each other? They look the same?
Yes.
Yeah, I kind of think they would, right? I think this is a pretty good tangent line, actually. I think, okay. I think this red line does look like the curve close to this point. Now, Colin, back to your point, you have a good objection though. You said, I don't think the tangent line should cut through the curve. And it shouldn't go from the bottom of the curve to the top of the curve. And in general, you are correct. Tangent lines will not cut through curves in general. There's one exception to that though, and that's an important exception. The exception is at inflection points. And I want you to notice that B, I think, is an inflection point, because notice the curve switches from concave up over here to concave down on this side. So at inflection
would you say
point,
that this is kind of exaggerated to make a point?
well, of course, yeah, it's in my notes, right?
Oh, okay. Okay. No, that's fine. If that's
So
what you want to do.
I'm trying to emphasize.
Got
okay.
it. Yeah, that makes sense.
But I would say, yes, I would say that's a fairly good tangent line. If someone had drawn that line, I would say, hey, you did a pretty good job of trying to draw the tangent line, which is not easy to draw by hand. And just back to your point, at inflection points, that's one place where tangent lines can cut through curves. All right. All right. Well, Colin, since I'm talking to you, what about C? Does that line look like does this red line look like it could be the tangent line at this point?
So then I'm gonna say that it does not look like an inflection point. So I would say it looks okay.
It looks okay. Yeah, I would say that too. Yeah, I think that's not a bad tangent line right here. Okay. Again, you're thinking close to that point, right? Does that line look like that curve? If you were to zoom in on this point, would you get that red line? I think probably you would get something close to that, right? Okay. What about D? So what do y'all say to D? Well, we just talked about this case a moment ago. What kind of point is D? That's a special point on the curve.
So local minimum.
Min.
It's switching from decreasing to increasing. So when you're switching from decreasing to increasing at a point, what's that point called? Begins with a T.
Tangent.
That's a type of line, but a type of point that begins with a T is
transition.
Y'all doing really good. Okay. Turning point. Yeah, this is a turning point, right? Remember that term, turning point? Okay, so this is a turning point. It's increasing, it's switching here from decreasing to increasing. And at turning points, tangent lines turn out to be what? What kind of line do you get at a turning point?
Horizontal.
Horizontal, that's right. You get a flat line. Yeah. At turning points, you get horizontal line. Well, this is a horizontal line that I've got drawn here at this turning point. So I think that's a pretty good tangent line there. Okay. That's a pretty good tangent line. So I would say to that is true. Okay. What about now the last one, E? So there's my point E. There's the line that I've got drawn at E. Does that look like the tangent line at E?
No.
Who's answering me there?
Mohammed.
Mohammed, what'd you say?
I say it doesn't look like a tangent line.
Yeah, it doesn't look at all like the tangent line, right?
Right.
Okay, yeah. This curve doesn't look anything, at this point, this curve doesn't look anything like this line, right? This curve is much steeper, right, at this point than this line is, correct? Okay, so that's a really bad attempt at drawing a tangent line. The correct tangent line would be much steeper, right? It would look maybe something like this, right? I can't even draw it, it's so steep.
Yeah.
Look, a much more vertical, right? than this line that I've got drawn there. So that's a really bad attempt at drawing a tangent line. Okay. Now, I listed here some facts about tangent lines, so I think that we already discussed most of these things about tangent lines, okay? But I want to point out one thing. Curves don't always have tangent lines at particular points. So you may not have a tangent line at a point on the curve, okay? Or at some x value. If the number, so at a number a tangent line will not exist if f of a doesn't exist, right? So if the number a is not in the domain of your function, you can't have a tangent line at that point, okay? You can only have tangent lines where the curve exists, okay? So at numbers that are not in the domain of the curve, obviously you don't have tangent lines. But another important criteria for having a tangent line is the graph has to be smooth and it has to be continuous at that point, okay? So if you have a curve that's not smooth, and I'm not defining this term, all right, so I'm leaving that as kind of just intuitive on your point, on your part, all right? But if you don't have a smooth, unbroken, got to be continuous, right? Got to be unbroken at a particular point, you cannot have a tangent line there, all right? So there are going to be some places on some curves where you don't get tangent lines, all right? You don't have tangent lines. And in that case, we say that the curve or the function is not differentiable. Okay, so there's a college word for you, differentiable. It's hard to spell, all right? But if you don't have a tangent line at a particular point on a curve, we say the function or the curve is not differentiable at that point. So if you do have a tangent line, we would say the opposite. It is differentiable at that point. Usually it's easier to say the tangent line exists than to use this long-term differentiable, which is hard to spell, but nonetheless, that's the technical term, okay? And remember, the instantaneous rate of change at a particular number is the slope of the tangent line at that number. All right. So I'm going to give you a really easy question here. All right. So look at this function. So this is a really a strange looking function, right? So this is completely made up so that, you know, as an example, I want to know at what x values does the tangent line not exist? So in other words, at what x values is the function not differentiable? Not differentiable. So let's just look here from left to right. So you see, if you're starting on the left here and you're just moving to the right, notice you have a nice, smooth, unbroken curve, right? So anywhere you have a smooth, unbroken curve, that the curve is going to have a tangent line there. So the curve is going to be differentiable. But where do we have our first break in the graph?
At the circle.
At this circle, which happens to be x equal what? -4?
-4, yes.
Yeah. So right there, we don't have a tangent line, all right? So no tangent line here because there's a break in the graph right there at x equal -4, okay? So you're not going to have a tangent line there. All right, if we continue, then, you know, again, see, we have this nice, smooth, unbroken curve. There's a special thing going on right here that I want to point out, but we'll get to that in just a second. So you still have a nice unbroken curve here, right? And that continues until you hit 2. And then, of course, what else happens at 2? What do you get in the graph? Obviously.
A break.
You get a break, right? So you see the graph is not continuous here at x equals 2, right? You get a break in the graph. So that means then that, again, you don't have there's no way to have a tangent line right here, right? So there's not going to be a tangent line at x equals 2. So no tangent line at x equal -4 because there's a break in the graph. no tangent line at x equals 2 because there's a break in the graph. And now continuing along to the right, you have a nice smooth unbroken curve, right? Until you get to this point. Now here, the curve is unbroken, but the problem is it's no longer smooth because look at what you have right there at x equals 6, you get a sharp turn in the graph. That is not considered smooth, okay? When you have a sharp corner point like this in the graph, that's not smooth. So here you cannot also have a tangent line. So there's no tangent line at either at x equals 6. You have to have smooth, unbroken curve to have a tangent line. Let me explain to you why this is, why you a little bit better, why there's no tangent line here at x equals 6. Let me show you what the problem is. The problem is different people might draw different tangent lines. You see, Damien, you might come in and you might draw the tangent line like this, you see, okay? And someone else might come in and draw the tangent line like this, and someone else may come and draw the tangent line like this. There's really no way of choosing one of those as being better than the other, okay? And the reason you cannot is because if you zoom in on this point, you're going to get a peak. You're going to get a point right here. See, if you zoom in on this little piece of the, graph, let's zoom in on it over here. You get like this. It's going to look like this. That's just not a straight line. See, there's no way you can zoom in close enough to this point on the graph that you'll ever get a straight line. You're always going to have this sharp point in it. Therefore, you cannot have a tangent line here, okay? So if you have parts of your graph that are not smooth, if they have these like sharp corner points on them like this one, you won't have a tangent line at that point. So that's kind of a rare occurrence, but you don't always have tangent lines at every point on every graph. Now, I wanted to point out something that's fishy about right here at x equals -1. We also have a problem with tangent line here, although the tangent line does exist. So you can draw a tangent line right here, and you're going to end up getting a vertical line. Right there at x equals -1, that curve looks like a vertical line. So it does have a tangent line, except it's a vertical line. But what is the slope of vertical lines? You recall from algebra what slope of vertical lines is?
Undefined.
It's undefined. So although you have a tangent line at this point, it's a vertical line. It doesn't have a slope. So any question where you are required to say the slope of the tangent line, you would say there's not one. So for instance, if you were asked, what is the instantaneous rate of change at -1? Remember, the instantaneous rate of change is the same as the slope of the tangent line. You would have to say, oh, that's undefined because the tangent line is vertical and vertical lines don't have slope. Here, you would also be in trouble if someone asked you, what is f prime of 6? What's the slope of the tangent line at 6? You would also have to say undefined because there just is no tangent line. It's not that it doesn't have a slope, it's that there's no tangent line at all, okay? So here you have a tangent line without a slope. Here you don't even have a tangent line. In either case, the instantaneous rate of change is going to be undefined, okay? Now, with just 1 minute that we have left, I want to yeah, no, I don't. Okay, so we'll have to take this up next time. This is going to take too long for me to explain. Okay, so we know now. But let's recapitulate here before we stop for the weekend. So we know now that we can find instantaneous rates of change at a point on a curve by finding what? The what?
Tangent.
The tangent line, and looking for what of the tangent line?
Oh,
Slope. Yeah, exactly. So remember, instantaneous rate of change is the slope of the tangent line. Okay. So the problem now with computing instantaneous rates of change is finding tangent lines, you see. Okay. If you can find the tangent line, then you can use its slope as the instantaneous rate of change. So the tricky thing here in computing an instantaneous rate of change, by the way, another term for that is derivative. So the trick in computing a derivative is finding the tangent line. Okay, that's the hard part. So that's what we want to take up next time is how do we actually find these tangent lines? Well, of course, one way we've done that, the only way that we've done that so far is by zooming in on the curve, right? Okay, but what if we cannot zoom in on the curve? So what if we don't have the technology or the means to zoom in on the curve? How do we find the tangent line? Okay, so what process do we use to figure out what the tangent line is at a particular point so we can compute its slope, so we can find the instantaneous rate of change at that point? So that question is what's going to obsess us now for a little while here, right? How do we actually find tangent lines, okay? So that we can compute instantaneous rate of change, or so we can compute derivatives. All right, we're going to start off with the simple-minded way of doing this. Well, I guess the simple-minded way is zooming in, but assuming that we cannot zoom in on the curve, the next simple-minded way is we're just going to draw the tangent line ourselves. So we're just going to look at the graph and we're just going to pencil in on our own the tangent line. So we're just going to draw our own tangent line, the line that we think is the correct tangent line. And actually, we can do that pretty good. You'd be surprised how accurate you are at that, okay? But you can't be completely accurate, all right? So we have to develop more sophisticated ways of finding the tangent lines other than just zooming in on the curve. But we're going to start with the easy way of we're just going to draw it ourselves, okay? So we're just going to imagine what we think the tangent line looks like. We're going to draw it in, and then we'll compute its slope, okay? And then that will give us our derivatives, our instantaneous rates of change. That's kind of fun, actually, okay? And not so difficult. So that's where we'll start. But then we have to pull out the heavy machinery of what if we want a really accurate answer, because we know answers that we get by drawing by hand are probably not very accurate. So how do we get really precise answers to, what is the slope of a tangent line? Okay, so we're out of time. Oh, good. I'm stopping at exactly the right time. All right. So you've got a homework due Saturday, right? I moved it back to Saturday, but you're well equipped to do that homework now. And I think you're really well equipped to work on the instantaneous rate of change homework too. Okay, but we'll answer questions about that on Tuesday. Anything else before we adjourn here? Okay, so I'm going to stop the recording, and so I will see you guys on next Tuesday. Okay. And start working on your sample test now. All right. Okay. So start working on that, so you have some progress on that, by next week. All right. So see you all then.